Hello, my name is William Chalk, and in this video, I'll be covering the calculus concept of optimization. I'll be solving number 9 on page 201 of the Nelson Calculus and Vectors textbook. In this question, we're asked to find the dimensions of a soup can so that the cost will be the lowest possible. The question reads, a soup can of volume 500 centimeters cubed is to be constructed. The material for the top costs 0.4 cents per centimeter squared, and the material for the bottom and the sides costs 0.2 cents per centimeter squared. Find the dimensions that will maximize the cost of producing the can. The key elements of this problem are the volume here, that is 500 centimeters cubed, the cost for the top of the can, and the cost for the bottom of the can. The steps to solving this equation are as follows. Develop an equation for each the top, bottom, and side of the can using the formulas for their areas and their costs. Express all of the values in terms of one variable. The volume will help with this. Combine each of the equations to get the total cost equation. Differentiate that equation. Solve for the zeros of the derivative, and use that value to solve for other dimensions of the can. So first, to develop the costs of each portion of the can, I'm going to multiply their costs by the formulas for the area. The top will be a circle, so the cost of the top times the area of a circle, the cost of the bottom times the area of the circle, and the side will be a rectangle where the width is the circumference of the circle, 2 pi r, and the length is the height of the can. And we'll take that and multiply it by its cost. Now, to express all of the equations in the terms of the same variable, our first two equations are only in terms of r, so it's good, but the third, we have an h in there, and we need to get rid of that. So we're going to use the volume of the can, which we know is 500 centimeters cubed. And the volume for a cylinder is pi r squared h. Now we want to isolate for h. So the h is equal to 500 over pi r squared. And we'll sub that back in to the cost of the side of the can to get 0.2 times 2 pi r times 500 over pi r squared. And we'll cancel out pi, cancel out one of the r's, and we're left with 0.2 times 1000 over r, or 200 over r. Combine our equations to get the total cost for the can. So the cost in terms of r is going to equal the cost of the top plus the cost of the bottom plus the cost of the side. So if we sub in all of our equations, we'll get 0.4 times pi r squared plus 0.2 times pi r squared plus 200 over r, and that simplifies to 0.6 pi r squared plus 200 over r, and this is the cost equation for the can. Our cost function looks like this. Now it's really zoomed out, the scale is really big, and I wouldn't be able to show any more if I wanted to try to encompass more of the graph. But there is an asymptote along 0, but really we don't care about anything to the left of 0 because the radius of the can can't be negative. So all we're concerned about is what's on this side of the y-axis. Now you can see here, this is the minimum point on the graph. This will be where the cost is the least. So the slope is going to be 0 here. So when we find the derivative will equal 0 at this point. And that's what we want to find, and that's how we'll find the lowest cost of producing the can. So now that we have the cost equation, we need to differentiate it. And we're just going to make it a little bit simpler to differentiate by bringing the r in this piece up into the numerator. So it's going to be 200 times r to the negative 1. So to differentiate, we're going to bring down the variable and multiply it by the coefficient. So 1.2 pi times r to the variable minus 1, so r to the 1, which is just r. And then we're going to bring it down minus 200 r to the negative 2, which simplifies to 1.2 pi r minus 200 over r squared. Now that we have the derivative of the function, we want to find where it equals 0, which we can see is right here. Now, at this point is where the cost of producing the can will be the least. So we want to put 0 in for our derivative and then solve for r. So 0 equals 1.2 pi r minus 200 over r squared. So 200 over r squared is equal to 1.2 pi r. So 200 is equal to 1.2 pi r cubed. And then we're going to divide 200 by 1.2 pi. So 200 over 1.2 pi is equal to r cubed. And then we want to take the third root to get rid of this exponent. So the third root of 200 over 1.2 pi is equal to the radius of the can. Consult the calculator, and we get approximately 3.76 is the radius. Now that we have the radius of the function, all we want to do is sub it back in to find the remaining dimension, which is just our height. So as you can recall from earlier, we have the equation that height is equal to 500 over pi r squared. So we'll sub in our value for r. So 500 over pi times 3.76 squared. And then consult the calculators again. 11.27 approximately. The last step is to write our therefore statement. So, therefore, the dimensions of the can that will minimize the cost are r equals 3.76 centimeters and h equals 11.27 centimeters. This exact type of math would be used by engineers responsible for making any type of container, such as soup cans or cereal boxes.